Oh, there are people who, okay, there are people who they have the system have to remove. I'm not sure why. Okay, but um, we see later. Okay, okay. Today we shall cover the other topic. Okay, biomedical. Okay, for biomedical electronics and bioinstrumentation. Okay, today we'll talk about the basic sensor principles about the temperature. Okay. So the content for today's lecture, actually, according to in our syllabus, actually these four, um, we will learn about these four. Okay, but I will add up about because just now in our tutorial, there's a question on the infrared thermometers. So I will cover that too. Okay, I will cover that too. I will try to have a slide on it. Okay. And um, I think this is very relevant. Okay, very relevant because now we are using radiation-based thermometer. Okay, radiation don't only think about X-ray, X-ray and so on. Okay, even our heat can be a radiation too. So okay, there will be four topics here: temperature measurements, okay, thermocouples, thermistors, and fiber optic sensor. So these three thermocouples, okay, thermistors, and fiber optic sensor is the sensor that we are going to use to measure our temperature. Okay. I love to make this what we call perumpamaan lah. I mean, uh, what differentiate the modern science and also because previously people have been looking to the nature for thousands of years. Okay, people have been looking to the stars. Okay, look at people have been observing many of oceans, skies, animals. Okay, plants and so on. Okay, so uh, what differentiate if you because all of us okay we have a tradition. Okay, if you look at uh, the sciences of the past. Okay, and for instance for medicine we look at the what type of herbs that can cure people. Okay, we look at the sky and that's why certain people uh, they even make prediction of the future because of that. Okay, although necessarily there's no even in Islam uh, we forbid it actually. Okay, we forbid the astrology and so on. Okay, but okay, I don't want to dwell about indulge in it further. Okay, um, if you look at the modern science, okay, you will see that modern science we look at the physics. Look at the physics. Something that maybe people before that doesn't observe. For instance, pressure. Maybe they observe, but they don't make it as a parameter. Pressure, okay, heat, all those things. Okay, pressure, like heat. What else? Uh, Force. Okay, all these things are physics. All those things are physics. Okay, okay. So that comes the beauty of it. Okay, because when you understand it, like for instance, pressure. Okay, you know that there is a increase of pressure. Okay, means okay, it can be good, it can be bad. Okay, for instance, like if for blood pressure. Okay, if it is low or if it is high, too high. Okay, um, you just imagine about the blood pressure. Okay, if a pipe, just imagine your pipe. Okay, the pipe it has been subjected to intense pressure. What will happen? Okay, it may burst. Okay, so this is also the same. Okay, people start to understand, okay, we have this, people have, uh, they compare, oh, this guy have a high pressure, this one have a normal pressure. So how they know normal or not normal? Because, okay, they measure it on the healthy person, and they measure, oh, the temperature is this 100, maybe, okay, now they use 120 millimeter mercury, okay, something like that. Okay, so for those who are not healthy, maybe up to 160, 180. Okay, so we start to understand that that blood pressure is one of the indicator whether a person is healthy or not. Okay, so what else? Okay, it has been like ages, huh? Okay, I think since maybe in the beginning, okay, people know that if a person having fever, okay, the temperature will go high. Okay, the temperature will go high. So this is one of the way, okay, to identify whether a person, okay, whether a person is healthy or not. And now because of the COVID, because COVID is one of those related to like fever, okay, related to cold, this like flu type of disease. So this type of temperature measurement will be more uh, will be more relevant. Okay, so so this there's a few questions there. Okay, I hope you can. I won't be answering all the questions inside the notes. Okay, inside the notes. But this and I also think that maybe some of the questions. Okay, I won't be asking in the quiz or in, but this is good. Okay, this is good for your thoughts. Okay. Okay. So let me see. Maybe somebody said that. Okay, that nobody comment anything. So I think everything's fine. Okay. Yeah. So we may relate it to many things. Okay, maybe infection. Okay, infection. Uh, so okay, maybe other type of body conditions. Okay, because you have a sorry. Okay, you have a different temperature. So that is why temperature is one of the critical parameter that we should watch. Okay, we should watch if a person getting sick. Okay, so this is something that biochemistry, biochemistry for us. Okay, um, we have learned about the enzymes and proteins. Okay, and they work the best at the body temperature 36.7. And you have to know that these uh, enzymes and proteins and other like, hormones and so on, okay, they can be denaturized. Okay, denaturized. They won't, when they're denaturized, meaning that the the structure have been changed, due to temperature, it won't be functioning. So that is why, okay, that is why we are worried about the high fever, okay, high fever and so on, because like if it is more than 41 degrees, okay, so that won't be good, especially if it has, especially if it happens to a baby, okay, child or toddler, okay. So even though like we start to acknowledge, okay, the uh, good things about, okay, about our like the biological systems. Okay, last time, okay, I'm not sure how many times I will repeat it with you. Okay, but last time when science advances, okay, like people, okay, even like especially in the 60s and 70s, okay, like there's an old series called the $6 million man. Okay, I I'm sure not. I'm sure that nearly majority of you doesn't never heard about this series. Okay, it's an old series. Okay, uh, the the hero of the movie of the series, okay, he has all his parts have been replaced by artificial hand, artificial everything artificial lah, okay, except for the head lah kot. Okay, so there is I think nearest, maybe not nearest, we can say that like you have seen like Robocop, maybe, yeah, if you switch on maybe HBO, maybe Fox movies, okay, sometimes they maybe you have watched this Robocop, okay. So in the past, people think that okay, if you replace, if you make a bionic man or something, okay, you will be better, you will be superior, more superior than other human, because you know, like if you are using metal parts and so on, okay, you will be stronger, okay, you'll be faster, huh? And so on, okay, like Superman, like even Iron Man, okay. But later we know that okay, our human body is a very complex and very and actually it's, yeah, it's superb, okay, it's superb, it's better that now people cannot uh, like if let's say you try to make a prosthetics or something out of it, definitely our human body can work better, much better, 1,000, 3,000, 5,000, 6,000 times better than the prosthetic, or millions times, million times better than the prosthetics, okay. So okay, so coming back to, here, okay. What happened here is that okay, um, we know that okay, if something happened to the enzymes or proteins, okay, what? Okay, then okay, I'm sorry, it's 3 o'clock. Okay, okay, so people see that okay, this natural things are much better than the okay, than the artificial, because we can compute better and so on. Okay, although that is the okay, I just remember what I want to say. Okay, although we have that, okay, although we have that point, okay, the point that actually the biological systems is more advanced than the artificial, okay, artificial silicon technology that we have and so on. Okay, we have a few restriction. Okay, it's about temperature. Okay, I'm not sure whether we have seen some anime last time, Japanese anime or you can see that the aliens always combine the technology, the bio and also the robotic technology, something like that. It's bio robotic, okay, because okay, but the problem is that it's about temperature. It's about temperature. So you just imagine if you want to have a system like much more complex than a computer, okay, and you want to fly out to Mars, okay, planet Marif, okay, you want to fly it, although it may helps better in terms of calculation and so on, okay, but the problem is that can the system survive in a high temperature? And usually, okay, just like example that I've given just now, okay, how if you have a if a person have a high fever or something, it will affect the total the total sanity, okay, the total the whole system of the body. So you won't get the you won't get the result that you want. Okay. So these are the things. Okay. The questions that okay, you don't have to okay, you don't have to answer this actually on paper or something, but just have a thought of it. Information. Okay. Like you know, when you have information, you have the visual, you have information, you have some. So the temperature will be higher in that area compared to the normal other part of your body, and then the temperature sensor to make sure that the infant in the better condition. Okay. Okay. So, why do we need specific body site for the body? Okay, like for instance, if you because of the accuracy to measure temperature. For instance, it's better to measure you're using your thermometer under your armpit, okay, and so on. So that is more accurate. Even like now we have for the radiation, the infrared, okay. I see. Oh, okay, 95 of you. Okay, I paste another link. Okay, for those who haven't signed the attendance. Okay. So we take the temperature from the head. Okay. So this okay. There are 3 ways. There's 4 ways. 4 ways actually, but I will cover the radiation in the async. Okay, today we will cover the thermocouples, thermistors, and fiber optic detector. Okay. I will look into the exam or the test. Okay. My tip is always to my students. Okay. Please read the less apa nama ni? The less the topic with the shortest note of all. Okay, that's one of my tips to start. Okay, I'm not saying that you shouldn't learn the thermocouple or thermistor. Okay, you must, because that definitely questions will come out from there. Okay, but to give you confidence, for instance, fiber optic detector is just around 3 pages. Okay, around 3 pages, so it's easier for you to read. Okay, and then it's easier for you to understand. Okay, okay, now we go to thermocouples. Okay, so this is some sort like okay, first of all, the definition. Okay, definition, how does it work? Okay, so how does it measure? Okay, how does it measure temperature? Okay, it converts thermocouples convert, okay, thermal potential difference to electrical potential difference. So see, so try to relate it. Okay, every time when you learn, okay, try to relate it with the previous notes. Okay, it's a transducer. It's a transducer. Why? Okay, because it converts okay, one measurement to electrical signal. So thermocouple is a transducer. So try to think like that. Okay, so throughout the lecture, okay, you have to know that okay, in the end of the lecture, what are the things that you have covered? What are the things that you have understand? What the things? Okay, so you can explain it. Okay, you can elaborate it. Okay, and maybe you can apply. Okay, so please understand the fundamental of it. Okay, so this is a bit of history. Okay. This thermoelectric thermometry, okay, discovered by Seebeck in 1821. Okay, 1821. So, 200 years ago. Okay, happy birthday, 200 years ago. Okay, so he observed that okay, this electromagnetic field exists across a junction of 2 dissimilar metals. Okay, so they observed that okay, this EMF, okay, it exists at the 2 junction. Okay, 2 junction of the 2 dissimilar metals. Okay. So now you see, okay, this T1, T2, okay. So here, okay. So all these points are important after this. Okay. There with me. Okay. So the phenomenon is the sum of 2 independent effects. Okay. EMF generated solely by contact of 2 dissimilar metals and the junction temperature. And then, okay, EMF due to the temperature gradients along each single conductor. So these two, okay, is the event, okay, that give the phenomenon for the thermocouples. Okay, first of all, the EMF generated solely by contact of 2 dissimilar metals. Okay, and the junction temperature. So you have two dissimilar metals. You cannot have similar metals. Okay, for thermocouples. Okay. And then the EMF, okay, due to the temperature gradients along each single conductor. So this effects, okay, this effect, okay, discovered by Peltier and Thomson. So you have this lot Kelvin Thomson Kelvin. So you have the Kelvin punya ni lah. Okay. Okay, so now we go back to Seebeck, 200 years ago. Okay, the Seebeck voltage is given by the following power series expansion. Okay, so this is the equation. Okay, the temperature is in degrees Celsius and the reference junction maintained at 0 degrees. Okay, the equation is curve fitted from the obtained calibration data. Okay, so this is how you get the equation. Okay. So, this is okay. Jadi sembang-sembang. Okay. So how do you get this? Okay. So, they don't get the equation just like that lah. Okay. They will okay make a measurement. Okay. And try to relate it lah. Okay. So when they do the measurement, when they do the experiments, okay, so they can see a series, okay, a series of the measurement, okay, measurement, like a series of readings, okay. There's a phenomenon. So it is like in order, okay, it is in order. So although maybe there will be a very slight difference and so on, but this is the thing that that governs, okay, that governs the phenomenon, okay. So it always be like this, like so for instance, V equals to IR, okay, V equals to IR. So it always like the relation between the voltage, the current, and so resistance, okay, it is always like that, okay. I know maybe there's certain phenomena, maybe at using different material, okay, maybe at a certain temperature, okay, but at the linear point, at the linear reading, okay, you will have this this characteristics when you do the measurement. Okay, we will see some interesting plots, okay, that will tell you more about this. Okay. Okay, so there are 3 empirical laws for this. Okay, so first, okay, this homogeneous circuit, then you have the intermediate metals, and then the successive or intermediate temperatures. Okay, so there's a circuit, okay, there's a metals, and then there's a temperature, okay, involved. Okay, first of all, the homogeneous circuit, okay, states that in a circuit composed of a single homogeneous metal, one cannot maintain an electric current by the application of heat alone. Okay, means that so there should be two, okay, two metal. Okay, single homogeneous metal. What does it mean? Okay, it's the same metal, no different at all. Okay, homogeneous, satu jenis yang sama, really homo satu lah kan. Okay, so it cannot maintain an electric current by the application of heat alone. Okay, so you need to be different lah. You must have a different type of metal. Then intermediate metals, okay, states that the net EMF in the circuit consisting of an interconnection of a number of unlike metals, okay, maintained at the same temperature is 0. Okay, states that the net EMF in a circuit consisting of an interconnection of a number of two metals lah. You say 2 metals maintained at the same temperature is 0. So there's a balance there lah. There's a balance there lah kan. Okay, if the same temperature, okay, they should be 0. Okay, then the last one about the temperature, successive or intermediate temperatures, okay, states that the EMF E1 and E2 are generated when the junctions are at T1 and T2. T1 and T2. Okay. Okay, so the thermoelectric sensitivity is represented by the alpha, okay, given by the alpha equals to A, okay, plus BT. So just have a look at the Seebeck. Okay, the form is nearly the same, but you you but you replace it with a constant, A and B, okay. Okay, alpha is not a constant but varies with temperature. So you have to remember that. Okay, alpha is not a constant, so it will be different. It will be different with the temperatures. Okay, and the sensitivities, this alpha is sensitivity range from 6.5 to 80 microvolt per degree Celsius at 20 degrees with accuracies from 0.25% to 1%. Okay, so means that it should be very okay accurate. Okay, so if you want to have a accurate reading, the reference junction must be kept at a triple point of water temperature. Okay, so you can achieve it by having an ice bath. Okay. Okay. So there's a question there. Okay. Now we have I hope that you can find so in the time of seaback, okay, people implement the ice bath, okay, to have the cold junction. That's why they have a term cold junction, because of the triple point and one of and then you have to create okay, and because of the ice bath you have a cold junction. Now how you make the cold junction? Okay, this is for if you are interested, if you are curious, okay, please have a reading. Please search it through Wikipedia or something. Okay. Okay. So thermopass are a combination of thermocouples, okay, connected in series to increase accuracy, okay, and then the thermocouple voltage can be so we can see that if you want to measure if you want to know the voltage of the thermocouple, we can check it, okay, we can check it using digital multimeter. Okay, so okay, this is about how you are going to record it and so on. Okay, advantages of the thermocouples. Okay, it should have a fast response time, small in size. Okay, the fabrication is easy and it is a long term. It is stable for long term because it uses metal. Okay, different type of metals. Okay, you can make it at a small size. There should be a fast response time. Okay, and the fabrication is not that difficult. So this is the attraction. This is the attraction of the thermocouple. Disadvantage, okay, because just now, okay, just like 60 microvolt and so on, a small output voltage, and then it has a low sensitivity, okay, and then you need the cold bath, the reference temperature. So these are the disadvantages, okay. In my questions, like for instance, okay, if maybe the issue of these disadvantages have been solved by using other types of sensor, maybe like thermistor and so on, maybe, okay. One of the way to look at the questions, sometimes the advantages, okay, the disadvantages, the disadvantages of okay, maybe sensor and so on, okay, can be an advantages for the others, okay. So please have a look. Sometimes we don't tell, sometimes the notes, okay, doesn't tell you straightforward. Sometimes you have to read between the lines, okay. But for this is clear, okay. It tells you about the disadvantages, the advantages and disadvantages straight to the point. Okay, so application, okay, you can make it, okay. You can make it make it small and then use it in catheters and hypodermic needles. Okay, so due to this, okay, that's why you can, that's why the maybe in terms of price it is more cheaper, okay. Okay, because of this issue. So whenever you consider incorporating sensors, you are going, sensors and so on. Okay, do consider about the how does this sensors produce. Okay, then that's why you know that okay, maybe this sensor is why this sensor is much cheaper and from the others, because maybe of the system and so on. So if that's why when you involve, like for instance in the IDP or maybe in your FYP in the future, okay, please have a look at this. Okay, maybe and then you understand, oh, this is the reason why this type of sensor, this type of maybe like components is much cheaper or much expensive than the others. Huh? Okay. Now we go to another type of sensor, which is thermistors. Okay. Okay, thermistors. Okay, it is made. It is a semiconductor. It is semiconductor made from same materials. Okay, there is a thermal resistor, so it resists the heat. Okay, the thermal resistors with a high negative temperature coefficient. Okay, so the principle here is that when the temperature increase, the resistance decrease. When the temperature decrease, okay, the resistance increase. So, okay, by knowing this phenomena, okay, people comes out with the thermistor. Okay. So the resistivity of the thermistor semiconductors used for biomedical application is between 0.1 to 100 ohm meter. Okay, so these are the range of the resistivity of the thermistor semiconductors. Okay, this is how a thermistor looks like. Okay, okay. So please, okay, always when you browse the your notes, okay, please compare. Okay, there's a difference of materials. Okay, thermocouples uses metal, thermistors uses ceramic. Thermocouple use metal, two metals. Okay, thermistor is from ceramic. So okay, because although this is a simple, just a simple what I call differentiation, okay, but this will make you understand, okay, how does this sensors work. Okay, advantages. Oh, it's quite fast. Okay, it tells you about the advantage in the beginning. Okay, let's see how many people are there. Oh, 98. Okay, tak ramai lah. So maybe something like somewhere like 10 people is missing. Okay, let's go to notes again. Okay, so thermistors, you can make it small in size. Okay, relatively large sensitivity to temperature change, extend long-term stability. So okay, so this is a difference between thermistor and also your thermocouple. So have a look again. Okay, thermocouple has a low sensitivity. Okay, thermistor high sensitivity, hence high sensitivity. Okay, but both have a long-term stability. You can have a look. Okay. So there's a difference and also similarity between these two sensors. Okay. So how does this thermistor works? So it is governed by this equation. Okay, RT equals to R naught, and then and so on. Okay. Okay. So we have beta. Okay, just now for for the thermocouples, okay, you have alpha. Okay, so here beta is important. Beta is the material constant. Okay, while T naught is the standard reference temperature in K. While thermocouple is measured like where we use degrees Celsius. Here we use Kelvin. Beta is known as the characteristic temperature increases slightly with temperature. Okay, so yeah, so now you have to ask yourself why we use thermistor as a sensor. So okay, through the lecture, okay, we will know why we're using it. Okay, okay. First of all, it's a ceramic. Okay, ceramic. That's the thing that also contribute to this application. Okay, beta ranges from 2500K to 5000K with typical value of 4000K. So this is the material constant. Yeah, the temperature now, just now we have the beta and now we have the alpha. Okay, alpha again. Okay, this is the equation. Okay, this is found by differentiating the empirical relationship, okay, with respect to temperature and further dividing with by RT. Okay, alpha is a non-linear function of temperature. Here is the it's a non-linear function of a temperature. Okay, so typical thermistor zero power resistance ratio temperature characteristic for various material. So these are the this is a plotting. At zero power resistance, okay, the thermistor is operated at a very small amount of power, such that there is a negligible self-heating. Okay, so this is the plotting. Okay, the resistance ratio, and then the temperature. Okay. Okay. So just now about the thermocouple, we have issue of self-heating. Okay. Oh no. Okay, I got confused with this one. Okay, sorry. There's no issue. Okay, sorry. Okay, the V versus I characteristic are linear up to the point where self-heating becomes a problem. So, okay, I want you to look at this graph. Okay, you can see that the about the linearity. Okay, okay. So at a certain point, okay, it is not linear. So when it is linear, then it is okay. It is okay for the for you to use the thermistor. When there's an excessive heating, okay, you can see that there's a excessive heating. Okay, the thermistor voltage, okay, the thermistor voltage it starts to go down. Okay, it starts to goes down, but the current, okay, you can see from the x-axis, the current increases. Okay, so this means that it is good if you know this characteristic. When there's a self-heating, it will be no longer linear. No longer linear. So at certain point, maybe like okay. So if after that, the if you still use the thermistor, okay, it won't be accurate. It won't be accurate. Okay. So maybe up to okay the measurement okay will be but okay will be good only up to like okay for 0.1 current okay like for 10 voltage 10 volts at 0.1 milliampere okay the reading is still good maybe up to uh, somewhere like 0.8 or something okay usually we just take this point lah okay so another material maybe okay maybe at 1 milliampere and then against like maybe you can say that maybe like 70 or 60 60 volts it's still good okay okay so it goes to what I asked you previously V and I VI characteristic okay it's a resistance kan V equals to IR so R equals to V okay divided by I okay the voltage divided by current so you can use the Ohm's law the Ohm's law okay and then maybe you can also observe the current time characteristic okay but that's okay okay we just concentrate on the VI characteristic plots okay so time delay for current reaching maximum value is determined by the voltage applied okay the mass of the thermistor and then also the value of series circuit resistance okay so the realization of the of the R and T characteristic, okay, use circuit schemes, and microcomputers, okay. So the circuitry for readout is the same as the conductive sensor. Maybe you can use also the bridge circuit, okay. And then if a very small difference can be found using a differential temperature bridge. So these are the things if you want to apply it. Okay. So we have some idea of how thermistors look like. So it can be in the form of like beads, okay, maybe in chips, okay, maybe looks like rods, washers, okay. But most common is the one that we have looked before. We have looked with. We have the first figure, okay, the glass encapsulated bead thermistor. And why? Okay, why is this package desirable? Okay, maybe it's more robust. Okay, it's more robust. It's easier. Okay, um, it will bake easily and so on. Okay, so and yeah, maybe you can produce it easier. Okay, and these are the reasons. Oh, our lecture today is bit fast. Okay, tak apa, we can finish it like 4 something. Okay, okay. So we have a glass coating protects the beads of the thermistor, okay, from hazardous environment from the body, okay, from the body without affecting the thermal response time. So it has a glass coating protection, okay, that covers the beads. Okay, small size thermistor allows application on catheters and hypodermic needle. Okay, so you can see in the thermodilation catheter systems. Okay, and then so you can also use the for the oral thermometer. Okay, the one that in the I think in the beginning of the lecture we have this typical oral thermometer. So this one of the application that you can use. Okay, we don't have much after this. Okay, now we go to the fiber optic. Okay, kita habiskan lah. Okay, I never thought it won't be, it will be quite fast. Okay. Okay, just 1 hour lecture. I thought that we can finish it by 5. Okay, but tak apalah. Hari ni kita habis awal. Okay, fiber optic temperature sensor. Okay, it's a small prism shape sample of single crystal undoped gallium arsenide is epoxy at the ends of 2 side-by-side optical fibers. Okay, so this is the gallium arsenide sensor. Okay, you have an epoxy, then you have transmission fiber, and then you have the reception fiber. Okay, and this is the diameter of it. Okay, okay. The sensor and fiber can be small. Okay, compatible with biological implantation after being sheeted. Okay, so this is intended for biological application. Okay, so for this case, it's for implantation. Okay, principle of operation. Okay, one fiber transmit light from light emitting diode source to the sensor, and it is passed to the gallium arsenide. Okay, sensor. Okay, and collected by the other fiber for detection. Okay, in the readout instrument. Some of the optical power traveling through the semiconductor is absorbed by the process of raising valence band electrons. Okay, across the forbidden energy gap into the conduction band. So it's about the valence band of the electron, and then the energy gap, and then the conduction band. So there's a physics behind it okay, how you can apply this, how you get your measurement there. Okay, okay, because the forbidden energy gap is a sensitive function of material temperature, the amount of power absorbed increases with the temperature. So this is how they relate. So that's why physics is interesting because you observe what happened to the nature, okay, to the material, in this case the material. Okay, so you can see, okay, you try to equate this. Okay, you try to make a formula. Okay, to understand how this phenomena happen. Okay, so if you know okay how much of the power absorbed, so it is it is increased with the temperature. Okay, application. Okay, nak ada okay, just one more slide to go, which is the reference. Okay, the non-metallic probe is particularly suited for temperature measurement in the strong electromagnetic heating fields used in heating tissue for cancer therapy or in patient rewarming. So these are the application lah. Okay, so you can find more applications. Okay, maybe you can find it in the internet. Okay, this is just a guideline. Okay, this is again not a guideline. This is just a guide. Sorry, not a guideline. This is just a guide. So if you want to know more about the applications, okay, maybe you can find it there in the internet. Okay, so for now there's a two. Okay, why? Okay, if if there's a strong electromagnetic fields, okay, so sometimes okay for cancer therapy, it has a it uses okay like it has a high strong electromagnetic fields, okay. So if let's say you want to measure measure temperature there, you need an alternative. So this fiber optic temperature sensor will be a good alternative. Okay then. Okay, we will end this a bit early today. Okay. Okay. So anything. I hope that okay you may find if the questions there can assist you. Can assist you in terms of what we call to appreciate the application, uh, the principle behind all this, the temperature sensors that have been introduced. Okay, and I hope that okay, um, during the examination, okay, you can have a good mark for it. Okay, so everybody, okay, thank you very much for your attention. Okay, I hope that okay, selamat buka puasa. Okay, nanti we will have okay sama-sama. Okay, we will have selamat buka juga. Okay, so at the same time next week, okay, we will go to the the origin of the biopotential and so on. Okay, thank you very much everybody. Jumpa lagi. Okay, Assalamualaikum.
Thank you, Doctor.
Sama-sama. Okay, I better